So we are looking at distinct roots and how to find them. So if you're going to do the distinct roots and you have a complex number, so many roots of a complex number, the first thing you need to do is make sure that right now this is in which form, rectangular or polar? Rectangular. It's in rectangular form, right? So what was our horizontal axis will be the real axis. We'd go right 2, and on the imaginary axis we'd go up 2 to plot our point. So that's a rectangular coordinate for a complex number. If we're going to find the distinct roots, we need to express this in polar form. The complex number needs to be in polar form before we start doing these things. Now, for our first one, we're going to do the cube roots. Notice the plural on there, cube roots. So that means that, well, when we go to do this, the value of p, and you'll be like, what the heck is p? P is the root, okay? The root number. So if it's cubed roots, p would be 3. If it's 7th roots, p would be 7. If it's 9th roots, p would be 9. N, which is going to be part of our formula, is all of those roots listed out starting from 0. 0 root, 0, 1, 2. We have to find this many. We keep going until we find the p minus 1 root. Why the p minus 1? Well, if I asked you to find the cube roots, there should be how many? How many should there be total for cube roots? 3. 3. Well, if I start at 0, right? 0, 1, 2, there's 3 of them right there. So if p is 3, I'm going to go up to 3 minus 1, which is 2. Okay? And if I ask you to find the 7th roots, or 7th roots, then you'd have 7 of these, but since we're starting at 0, I'd go from 0 up to 6. That would give me my 7 roots. And so here's the formula that we use as long as it's in polar form, and we have to do this formula however many times. Whatever the number of p is, that's the number of times we have to use this formula and calculate each of these. So here they are. R to the power of 1 over p times. All right, remember I said it would be in polar coordinates? It's going to kind of look like a polar coordinate, except we're going to have something different inside the cosine than just theta. And that'll be plus I sine of that same thing. Now, I'm going to write it in here, but technically I actually find what this is going to be before I start writing this as I do each root. So what goes in here is theta plus 2 times n times pi all over p. Theta plus 2 times n times pi all over p. That's how we're going to find it for each root that we're finding. When we go to find the 0, n will be 0. When we go to find for 1, n will be 1, and so on. And this will get us all of those roots. So in our first example, it says example 1, pth roots of a real complex number. Find all the distinct pth roots of the complex number. Find the cubed roots of the complex number 2 plus I, or 2 plus 2I. So what that means is I'm going to start with, I actually want to zoom out because I'm going to need the space. All right. First off, that's not in polar form. So my very first step is going to put it in polar form. So I need to know, in order to do that, I need to know what the radius is and what theta is. Anyone remember how to find the radius? For any polar coordinate, but if it's a complex number in particular. Square root of x squared plus y squared if it is a coordinate. When it is a complex number, we do square root of a squared plus b squared, just like when we do vectors. So it'll be 2 squared plus 2 squared, 4 plus 4 is 8, so our r value is the square root of 8, which is exactly 2 square roots of 2. I don't know that that will matter as we go on, because as we find these, things are not necessarily going to be on our unit circle. They'll look like they will be initially, though. So for our polar form, we have 2 square roots of 2 for the radius, cosine of some angle, plus I times sine of that very same angle. How do I find the angle? Same way we found it for, theta equals tangent inverse of b over a, or y over x if it's just a regular point. But if it's a vector or a complex number, it's b over a. And so in this case, it's 2 over 2. Tangent inverse of 2 over 2. I notice that they're both positive, so I don't have to worry about the sign. But I also notice that 2 over 2 reduces to tangent inverse of 1, which is located where on our unit circle? Pi over 4. Yep. So 5 pi over 4 would be it if both of these were negative. But since they're both started out as positive, it's pi over 4. So we are in quadrant 1 if we were to graph this in the complex coordinate plane, so we're going to go with pi over 4. So our angle is pi over 4. So here's that exact same complex number expressed as a polar coordinate. R times cosine obviously is the x value, or the horizontal value. R times sine theta being the vertical value when we graph that in the complex number plane. Now we have to find the third roots of this number. So the first thing I'm going to, now that I have it in polar form, I'm going to say, okay, p is 3, and n, that makes n 0, 1, 2. I'm going to have to do this 3 times. The first time I'm going to make n 0. The second time I'm going to make n 1. The third time I'm going to make n 2. And I'm going to have to find theta each time as well. So I'm going to pay attention to how I find the value of r and how I find the value of theta when I go to find these roots. Here's the other thing. This is in which form? Polar. But this started out as a rectangular number. So I'll have to put it back to a rectangular number when I'm done. So right now I'm just going to set these up, find the value of r that I'm going to use and the value of theta to make it go quicker when I actually go to calculate it. So for our first one, we have n equals 0, which means that r equals 2 square roots of 2 to the 1 over p, which is 1/3. And that's going to be the case for all of these. If you look at our formula up here, r is always raised to the power of 1 over p. So we're okay there. That's going to be the case for all of these. So when n equals 1, r will also still be 2 square roots of 2 raised to the 1/3 power. When n equals 2, r will still be 2 square roots of 2 raised to the 1/3 power. What's going to be different is theta, though, because theta is theta plus 2 pi, or plus 2 times n times pi all over p. Well, for this one, that's going to be our current theta, which was pi over 4, plus 2 times 0 times pi, which means that part goes away, divided by 3. So that's really going to be what? Pi over, not 7, pi over 12, because they had to multiply the denominators, right? So pi over 12. So I've got pi over 4 times 1/3, because that's 0. When I go to find the next root for the value of n equals 1, I actually have pi over 4 plus 2 times 1 times pi, and then I have to divide by 3. So 2 times 1 times pi is 2 pi, which I could rewrite as 8 pi over 4, which is going to make that 9 pi over 4. When I put that over 3, it becomes 9 pi over 12, which if you want, you can reduce. Theta is going to be 3 pi over 4 for that value. but 9 pi over 12 is what it would have started as, so I reduced it. Go ahead and find theta for the next one that we're going to calculate in just a second. We'll get to calculating these 3 roots. No, not 6. It's a 2 plus 4 pi over 3. So this is going to be 16 pi over 4, which becomes 17 pi over 4, which, when I divide by 3, becomes 17 pi over 12. Any questions on how we got that? So as long as we have our values for what the radius is going to be and what theta is going to be, we'll be able to calculate all 3 roots when we're looking at the cubed roots of this complex number. So now I'm just going to plug it in. This is going to be our value of r, which we've done as r to the 1/3, times cosine of our theta. And we're actually going to write that, and then we're going to distribute it so that we can get it as a rectangular, in rectangular form. So I'm going to have 2 square roots of 2 to the 1/3 times cosine of pi over 12 plus I sine pi over 12. And then I'm going to take my calculator and put that in the calculator. So let me freeze the screen up there for you guys while I grab my calculator, and then I'll distribute this. So in my calculator, I'm going to go and do second quit. I'm going to make sure I'm in radian mode, because these are in radians, not degrees. And I'm going to do 2 square roots of 2. Whatever that value is, I'm going to raise it to the 1/3 power. I'm going to take that and I'm going to multiply it by, oh, actually I wanted to do it all in the calculator at once. Let me just do that again. Let me unfreeze it. So in parentheses, I'll do 2 square roots of 2. Shoot. Wrong button. Raised to the power of 1/3. Oops, not underneath though. Raised to the power of 1/3. I did need to close this though. Times cosine. Once I do this once, it'll be easier to get the other ones. Times cosine of my angle. And our angle right now is pi over 12. So I'm just going to do pi over 12 and hit enter. So this will be the value of A. This gives us 1.37. And then I do second enter to re-enter it, but this time I don't want it as cosine, I want it as sine. And so that's going to give me plus 0.37i, because the I is attached to the sine. Even though it's not in the calculator, it's attached to the sine, and you can see that here. Right, there's the I times sine. So when I did this times sine, I distributed this to both in the calculator. This is what I got as one of my roots. I have 2 more to calculate. The good news is if I've already written them out like this, I'm just going to keep copying and pasting and changing the angle that's in cosine or sine. So for this one, it's going to be 2 square roots of 2 to the 1/3 power times cosine of 3 pi over 4, which actually is on our unit circle. I should have probably have the exact values for these. Times sine of 3 pi over 4. Let me grab it from the unit circle this time. All right. So 3 pi over 4 has a value for cosine of negative square roots of 2 over 2. That was not on, the last one wasn't on the unit circle, so we had to use our calculator. This one is plus I square roots 2 over 2. And I'm distributing whatever this is. I actually could break that down if I wanted to. I'm going to come back up to here and look at it as the square root of 8, which I could rewrite as 8 to the 1/2, is now raised to the 1/3 power. So what's that really? 8 to what power? 8 to the 1/6. So that's actually, yeah, that's not going to help me much. So I'm still going to end up having to do a decimal value because I can't break down 8, 6, do the 6th root of 8. So we're just going to distribute this anyhow. If I could do that, I would do that and get the exact values. So back to my calculator. We're going to plug in second, enter. I already have the radius set up in there, which is nice, so I'm going to just click cosine, and this time I'm going to click second insert because I want 3 pi over 4, which I guess I could have put in as 9 pi over 12, but I didn't. That's fine. So that's going to be the value of A, which is -1. And then I'm going to hit second enter and change it to sine for the imaginary part, which gives me +1 I. I feel like it should have worked out. The 6th root of 8 should have worked out if it's going to do that. For when we multiplied, but anyhow. So this is what I have as my answer for that part, for that root. And then I have one more root to go, which means I'm just going to repeat this same exact process, but with this value of r, so 2 square roots of 2 to the 1/3. This will be my polar form of the answer. Cosine 17 pi over 12 plus I sine 17 pi over 12. There's my polar form of the answer. We need to get it in as a rectangular form. So I go back and do second enter. I've got to change this back to cosine again. And this time it's second insert, because I need it to be 17 pi over 12. So that gives me -0.37. And then I repeat it, but I put sine in instead. And we have negative, or minus 1.37 I. So in rectangular form, our answer looks like this. So there are the 3 roots. If I zoom out a little bit, there are my 3 roots of this complex number. I still can't see it. So we have this complex number. It does take time.
Imagine if it's not a cube root.
That's not always. But so rather than repeating this every time from start to finish, I try to set it up. So I just have to hit second in my calculator and change the values. And then I can get the numbers pretty quickly at the end. Yes?
Earlier you're talking about doing the exact values.
Yes.
Like, do we have to do that?
So you're supposed to when it's on the unit circle. 17 pi over 12 isn't. Pi over 12 isn't. 3 pi over 4 is. And I do believe that square root of 8 could have been broken down better than what I did. I didn't do a good job of it. I would have been able to distribute. And you would have gotten this either way. So you're going to be okay for that for now. Okay? Yes? Yeah. All right. So flip the page. Try the next one. That's why. Let's take a look. So you actually, if you did this, if you set this up, you know that P is 4. We're going to find these 4 ones. I need to know theta when n is 0, theta when n is 1, theta when n is 2, theta when n is 3. The value of r was the square root of 8 because it's -4 square roots of 3 squared plus -4 squared. Take the square root. So then I do 8 to the 1/4. That's going to be the value of r to the 1/4. That's what we're going to use as we calculate these roots. Theta, however, is tangent inverse of -4 over -4 square roots of 3. What is that really? It's tangent inverse of 1 over the square root of 3, or square root of 3 over square root of 3, right? Which is on our unit circle. Tangent inverse of square root of 3 over square root of 3, or square root of 3 over 3, is right here at pi over 6. But is that where our angle is? What quadrant is this in? If it's -4 square roots of 3, -4i, it's in quadrant 3. Well, here's the thing. Those started out as negative. When you divide by negative, you have to do what? Add what? Pi. So if I'd evaluated this and said, oh, because it's 1, or because it's 1 over square roots of 3, that's going to be at pi over 6, I have to add pi units to it to bring it around to 7 pi over 6 to give me the actual answer. So 7 pi over 6 is our initial theta. That's for this point in coordinate, or in polar form. But that's not what I'm going to use here. Here I have to do 7 pi over 6 plus 2 times 0 pi all over what? All over what for this one? All over 4, yep, all over the value of p. And this one will be 7 pi over 6 plus 2 pi all over 4. And this one will be 7 pi over 6 plus 2 times 2, which is 4 pi all over 4. This one will be 7 pi over 6 plus 2 times 3 is 6 pi all over 4. So it's going to give us our different values of theta. This one's just going to be 7 pi over 24. This one's going to become, what is that? That's going to be 12, what is that, 12 sixths? 12 sixths plus 7 is going to be, is that going to be 19 pi over 24? Is that what you guys got? Or not yet? This one is going to also be, this time it's 4. 4 pi, 4 times 12. What's that going to be? In terms of 6, I'd multiply them both by 6. Will be 24 pi, no. Yeah, 24 pi over 6. Yes. Add 7. You got 30. Sorry, my brain's not working. What's 24 and 7? Thank you. 33, right? No? 31. 31. 31 pi over 6, but then over 4 is going to also be 31 pi over 24. This one times 6 is going to be 36 pi, plus 7 is going to be 43 pi over 6 times 1/4 is going to be 24. So there's our values for theta. Those are our values for theta. I'll zoom in a little bit. And you're going to see if you can use those to calculate, using the formula, r to the 1 over p times cosine of theta sub n plus I sine theta sub n for each one of these. So this is the theta for 0, the theta for 1, theta for 2, theta for 3. You're going to plug those in and see what values you get. I'll come back to you guys in a second. All right. So these are the answers that you should get. You guys will see them in a minute. I know you're still working on them. And that's when you plug this times cosine of this in, you get this. This times sine of this, you get this. There are the 4 roots.